Okay, so if I can just stop you where you are and ask you to turn to page 30, when we talk about half-lives. And even though I said before that with spontaneous decay, we said that this meant that we didn't know when any particular individual isotope was going to decay. Okay, it happens randomly. So we can't induce it, we can't prevent it from happening, and it just happens whenever it's going to happen for that particular unstable isotope. However, in general terms, we can make predictions because what we can formulate is a decay curve, and this decay curve is unique for each different radioactive isotope. The way we talk about the rate of decay is in terms of half-lives. If you look at the table on page 30, you can see that calcium-45 that's used to study plant nutrition has a half-life of 152 days. Carbon-14 has a half-life of 5,760 years. Cobalt-60, 526 years. So there's some long ones, but there are some shorter ones as well. For example, the sodium-24 that has a half-life of 15 hours. The half-life, and therefore the decay, the spontaneous decay, is unaffected by temperature, pressure, or any state of chemical combination. So it doesn't matter what compound that radioactive isotope is in, it will still decay as it was going to decay. We cannot chemically react radioactive atoms to make them stable or harmless. The only thing we can do is to contain them or dilute them to reduce their impacts. Now on page 31 you can see this is a representation of what the half-lives mean in the context of decay. This whiteboard marker is looking a bit sad, so I'll change over. We have this is time on our x-axis, and that this will change.
So some of these half-lives are like hundreds or thousands of years. How did they know that if they could actually like go through a half-life?
They can't get through the whole lot. Yeah, because in actual fact, you get a lot of information right at the beginning of a decay process. If we look at, we also have the shape. It's the same shape for every isotope. In that if this is 100%, our starting amount is 100%. It could be a gram, it could be 10 grams, it could be giving us a guidance in counts or emissions. It's just somehow or other what's happening. And what I'll know is that at 50, whatever time that is, that's the time for the first half-life. Okay, when I have only got 50% of my original isotope remaining. So we don't have to go through a whole half-life to work out when that's going to be. We just need to be able to determine the rate early up there. And so if I get to 25 here, then this is the second half-life. because I'm halving 50. Okay? This is half of 100. That's the first half-life. Whereas 25, here is half of 50, is for the second half-life. And these are going to be the same length of time. If I was able to draw a nice diagram, they would be the same size. Okay, so that we end up with this same shape for every radioactive isotope. And there's an illustration of it on page 31 as well, where you can see if all those dots in the very first square represent all of the radioisotopes that are present at time equals 0, whenever that might be, then after one half-life for that isotope, the second image is representing, well, how many are still radioactive. And then as we go on, it doesn't have every single half-life because the next picture is 4 half-lives. So we've skipped the second and the third, but there are many fewer radioactive isotopes present. Until we get down to, if we think about 10 half-lives, then we're in the region of background radiation. And we can't then determine what radioactive emissions are coming from our isotope or the background. Like, we can't really tell. We would then consider that it is no longer radioisotope. Most of them are gone. Okay, so what else do we need to say about it? When I'm talking about percent here, or if it was mass or if it was emissions, doesn't really matter. But if I've decayed to 50%, this doesn't mean that 50% of my mass has gone. It means that 50% of the original radioisotope has decayed into a daughter isotope. Plus energy, okay? So it's not like it's disappearing. It's not like our mass has gone away. If I had have talked about this as being 100 grams of my original radioisotope, that doesn't mean now that the container weighs 50 grams. Okay, that's not what that's saying. That's just saying that at this point here, when half have decayed, that we've got half of our original radioisotope and half of the new daughter isotope present. So the mass is pretty much the same.
Will it remain, like, so when we get to 10 half-lives, so if we had 100 grams at the start, would we still have 100 grams?
Pretty well, yeah. Obviously, if it's gamma, we would definitely have 100 grams. Depending on the length of the half-life for that radioisotope, then like, who knows? You might be able to measure it. A physicist in a fancy lab might be able to measure some mass difference, but by and large, no. We're not going to be able to measure that loss. Yeah.
So if this is like alpha, like decay, and it like released the hydrogen nucleus,
Helium.
Helium, how does it stay the same if it's like releasing?
Because
weight?
compared to the mass of the atom, even losing a helium nucleus isn't significant. But if this was in a container as well, then all of all of the released particles would be still in that container if it was an alpha particle, an alpha emitter. They would be contained in there as well, even if they weren't
Together.
part of the original. Like they might be stuck in the walls of the container.
So if this was like out in the open, there's a chance that
Well, over a long period of time, eventually you would be able to measure a mass difference. But yeah, we certainly wouldn't be able to measure mass differences in the context of a lot of the radioisotopes that we would come into contact with. And obviously there would be no mass difference for a gamma emitter. Yeah? Okay.